Okay, so here we're talking about the study I assigned to you about, you know, all these studies about secant, right? Cosecant. These two functions, I believe, is rarely studied at this detail. Okay, I bring this up is not because, you know, you're going to use it extensively. No, it's not because of that. It's because I want you guys to further understand what we talked about in class and apply it to different functions, right? For example, in the situation of secant, right, we know it's 1 over cosine. It's 1 over cosine. And so the denominator cannot be 0. So the, you know, cosine A cannot be 0, right? Cosine A cannot be 0. And the consequence would be A must be all real numbers except the odd number multiples of pi over 2. You got that, right?
Yeah, x can equal 2k plus 1 over pi over 2, where k is an integer, and where
right.
k is an integer.
Right. And range is a little tricky.
What I got,
the range?
Yeah, what I got is bracket 1 to infinity, and then add a little u sign to negative infinity to -1 bracket.
Okay.
You want me to try typing it out?
Yeah, I'm trying to, if you say it again, 1 to infinity.
And then the u.
Union.
To parentheses or little thing, no, yeah, that like that one. To negative
infinity to
-1.
-1. Very good. Very good. That's correct. But how did you figure out?
Oh, I looked at the graph and I kind of simply did it over there from there. And I also and I kind of want to make sure I was correct. So I went to the study center for math to see if I was correct at all.
Good. Very good. You just try to use all the resources, right? To get this. And in fact, all of these are from the definition of secant. Right? If you go back to the definition, that is the source of all of these forms, right? Of all of these forms. So we go back to ARD, right? We go back to ARD, right? A is angle measurement, reference angle, you know, definition. When it comes to secant, we pick that point, right? We pick that point XY on the terminal sides, right? On the terminal side. Of the angle, right? Of A. So what happened is that we have that picture, right? We have that picture. Let me go back to the number 30th. We have a little picture I want to bring to us. Right, we have that picture we want to bring us. Okay, so we're going to bring that picture over here. So we go back to the definition. What's the important thing about the definition, right? So we look at that definition. Right, we look at that definition. Why do I take that picture? Even though it works, it's just not the best picture. Wait. Okay, so I'm going to grab another picture, which is they're all fine, actually. I shouldn't be so picky about which picture. It just yeah, this picture is easier to explain. It's just a bit easier, okay? Where it doesn't matter which picture, so I have both pictures here. So this, we know that this point is x comma y, and this is the radius is the r, right? And all that story behind us, right? We have that stage. We are on the stage, and the definition would be r over x. Okay, and what is r? What is r? R is, right, the denominator is x. The r is what?
Would
The
be the
R is
reference
what?
angle. Would be the reference angle.
It's x squared plus
Oh,
y squared, right?
it's that.
Okay. So I'm going to show you some algebraic deriving from this process. I think this piece of technique will be very, very useful for you guys. Will be very, very useful for you guys. Okay. So we understand that this piece, right? From the surface, you can tell that, you know, geometrically, right? Geometrically, you can tell that the X is the green. I'm sorry, the X is the blue, the Y is the red, right? So we're consistent with that unit circle thing we talk about, right?
Mhm.
The blue is the X, the Y is the red, right? No,
Yeah.
am I right? No, I was wrong. The red is,
The X and the blue is the Y.
that's right. We don't want to mix that up, right? Because even though you can understand, I just don't want to add another layer of confusion, okay? So this is the Y. Y is the blue, which is consistent with the picture, right? The
Mhm.
X is the red, which is the X. Okay, we want to be consistent with that. Okay, we want to be consistent with that. Geometrically, you can see this is R over X, right? So this is R, and this is X. You can see R is always at least X, right?
Mhm.
Yes? Because R is X squared plus Y squared and taken square root. So this piece is always at least the same as X. Of course, X can be positive, can be negative, right? So in other situations, it could be, you know, on the second, on the second quadrant, X could be negative. So I'm gonna modify this picture. Okay. What did I do? Not this one. Yeah. I'm just going to make a little bit modification to show you that X can be positive or negative. Come on. Hey, come back. All right, right? So what you see here, okay, I need to bring that green light, the green one over there. The green. Oh, there. That's what I forgot. Okay. So this piece. So this two picture basically show that X can be positive, X can be negative. In the second case, you can see that, you know, the red would be this piece, right? And the blue would be that piece. You follow me?
Yeah.
Right. So X can be positive, X can be negative. So as a numerator, the numerator is taken square root of X squared plus Y squared because the choice of X, Y, the top is always positive. The bottom could be negative or positive. Okay. The bottom could be positive and negative. And if this is reflected on the picture of the unit circle as we know it, I'm going to put it right next to it. And you will better understand what I meant. Whoops. I don't like that, but you got it, right? You got it. So the red and blue and so on and so forth. So that's reflected on the picture. If you look at the X number red, right? The red, you look at the red, right? Those are the axes, right? So sometimes these reds are positive, 0. Sometimes these red are negative, right? You see the red can be positive, negative, right?
Yeah.
So that's what is reflecting. And these are the special cases on the unit circle. And of course, we have selected the unit circle. So the radius is 1. The radius is 1, right? With that said and done, okay, so I'm going to clean this up. I want to show you the following algebraic expression, which is going to be very useful for you. This expression, I can say is going to be less than or equal to this guy. I'm sorry, greater than equal to. The square root of x squared is less than or equal to x squared plus y squared. Do you agree with that?
Yeah.
All right. If we agree with that, right, what does this guy equal to? Equals to absolute value of x, right? Right? Yes?
Yeah.
Now, from here, because we're trying to figure out the range, suppose x cannot be 0, right? From x cannot be 0, we already figure out the domain, right? Because when x equals 0, that's something we cannot be, those angles cannot be in the domain. So now we come to this point that our goal here is try to figure out the range. So I'm going to give you the algebraic form, which I believe this form will help you when you're in calculus class to manipulate these, inequalities. So what I would do is if I divide both sides, because this is a non-negative, this is non-negative as well. So what I would do is that if I divide both sides, okay, so if I would divide both sides by, well, let me do this, okay. This is also saying, okay, the x is less than equal to, greater than equal to this guy. I'm going to do it this way. So x is between negative of the radius and the positive of the radius. You follow me?
Yeah.
On the unit circle case, this guy actually is equals to 1. If xy is on the unit circle, so let's keep it simple. Let's do that, Jacob. Okay. If this guy is on the unit circle, okay, so this guy equals to 1. So this guy equals to 1. Now, what does that mean? X is between -1 to +1, which is shown on this picture. Do you guys see that? Do you see that?
Mm-hmm.
If x is between -1 and 1, okay, if x is between -1 and 1, what if I have, because this piece now, because we have it on the unit circle, this is just 1 over x, right? Yeah. 1 over x, right? Because that's on the unit circle. Unit circle, right? So let me put it over here. Okay, so we have this form. So x is between -1 and 1. You agree with it. But from here, right? From here, if I flip it, okay, what will be 1 over x? Okay, I can flip it on this side, okay? Because both are positive, so I'm going to flip it 1 over absolute value of x. Okay, and this 1, I will flip it like this, 1 over 1. It's going to be greater than or equals to 1. Do you see that?
Yeah.
Okay, so 1 over, right? So this piece, I just put it next to it, right? We're not going to use it for now, right? That's obvious from the unit circle. So now we look at 1 over x, right? So the absolute value of 1 over x is going to be what? Is this absolute value is greater than equals to 1. What does that imply? 1 over x is secant. 1 over x is secant. Do you see that?
Yeah.
So the absolute value of secant, right? So if I replace it, why this come here? So if I replace 1 over x by secant a, what do I get?
You get absolute value of secant A.
That's right. And that's exactly the range you just described. Which is that? Okay.
So in other words, you can also say, and this is for the A, right? The little A thing, A into question mark.
This is for all the angles in the domain of secant. Okay, for all the A's in the domain of secant. In the domain of secant.
So this would be the domain then.
That's right.
This would be the other domain.
This is the inequality form of the domain.
Yeah, it's the little A that equals to the question mark, right?
Right. This is the inequality form of the domain. These forms are often used. You can look it up, but this form is not addressed enough.
So would you want us to use the one you just highlighted?
You should know both, but when you do algebraic manipulation, you need the first one.
I see, okay.
Okay. A lot of our students in calculus class, they cannot manipulate inequalities because they miss these bits and pieces.
Mm-hmm.
When they come to inequality, they're at loss or they make all kinds of mistakes. We actually haven't reviewed that absolute value inequality part. We will. And that's a huge area. That's an area of huge problems for a lot of our students. Mm-hmm. Right? Do you understand what this means?
Yeah.
Right? So because from here, you basically would be able to see, okay, secant A would be either less than equals to -1 or secant is greater than or equals to +1. Right? Remember, you recall that in your previous experience, you might have solved inequalities like that. Okay, solve inequalities greater than equals to 1. Okay, this is a kind of, it's come after, our current topics. Right? What is the solution to that? Right? We don't use x, so we can, well, we can use x, but this x is different from the x above. Okay, so I'm gonna use heart. Okay, what does that mean? The heart would less than equals to -1, or truth table kicks in. Truth table kicks in, greater than equals to 1. In graph, okay, let me draw the graph for you. Okay. I'm going to draw the graph for you. Right? This graph, in the graph, it means okay, allow me time to do this right. on the number line, if you look at the graph, right, it's going to be, come on. The software is, I'll get it here. So on the graph, okay, so I'm going to plot that picture here. You have for less than equals -1, greater than equals to 1, what it means is that red, okay. Never mind. I'm going to set the,
Yeah.
I'm going to set the interval properly. Okay, so that you see that red, that's the less than equals to -1 piece. And the other piece, okay, the other piece is, I'm going to make this piece thicker. And the other piece I'm going to get to show you is that. Oh, these two pieces. And also they include the points at the endpoints. I believe you might be familiar with these. And the red dot. That's the piece. Wait. I didn't put a red dot for me there. Oh, dot. Okay. So that's, you probably are familiar with this graph, don't you? So this inequality refer to the picture that the heart, okay, this is where the heart is. Okay, this is where the heart is. Okay. The heart is either less than equals -1 or larger than equals to +1. That's what it means. You got it, Jacob?
Mm-hmm.
So what do we have explained here is the range of secant, how you can derive the range of secant from its definition. It's algebraic form. I was just giving you the algebraic form of how to do it.
I see.
That's the algebraic form. You know, and this kind of little, you know, algebraic technique is very useful for you. Okay. Now let's go back. You get it? X-intercept,
Yeah.
Y-intercept, X-intercept, Y-intercept. So what have you, we're going to come to this place later, okay? We're going to come to this last.
Okay. So for the x-intercept, I got there are no x-intercepts, and for the y-intercept, it is 0,1.
Okay, you said there's no X-intercept. Why there's no X-intercept?
Because it never crosses or never goes on
That's
the
right,
x-axis.
because the output is always, the output is either above 1 or the same level as 1 or below -1. So there's nothing in between, right? So
Yeah.
there's no X-intercept. That's very good. Okay, how about the Y-intercept?
It would be 0,1.
That's right, you just plug in the 0, right? Plug in X equals 0. So plus A equals 0, when A equals 0 and equals 1. So now comes to the limit form. Okay, comes to the limit form. You know, when you are in calculus class, you will realize that there are a lot of points that in your consideration for specific functions that, you know, the function works very well. But we tend to consider those problem points. We tend to consider those problem points. So what are the problem points? Well, the problem points is when we get closer to the border of domain and non-domain.
Mm.
You know what I mean?
Yeah.
For example, domain and non-domain here is that we know that between, because we cannot assume the odd number multiples of pi over 2, right? So in the neighborhood of pi over 2, well, the odd number multiples of pi over 2, that's the places we're going to spend more time on, because those are the problem places.
Uh,
You got that idea? And it's always like that. It's always like that. Okay, always
okay.
like that, because the rationale is that, oh, we understand the situation when where there's no problem. Let's look at the problem points. So we kind of focus on that problem points because we know the other points have no problem. They're continuous, we can just plug in, no problem, right? So for that reason, you can see if we put these numbers, right? If you look at these odd number multiples of pi over 2, you look at the adjacent problem points, right? You have a negative pi over 2, pi over 2, 3 pi over 2, and so on and so forth, right? You probably have seen the secant curve, right? You've seen the secant curve. So what will happen is that you're going to consider, first of all, you may consider what happens in the neighborhood of pi over 2. To the left, to the right. You understand what I'm saying? So it could be from smaller than, it could be from larger than, but this is really a very much, kind of calculus content, because you're going to see a dynamic process there. You're going to see dynamic process there. Take this one, for example. When x approaching pi over 2 from smaller than pi over 2, what will happen? Well, you'll be dealing with something like this, right? Right? A is approaching pi over 2. And cosine at pi over 2 is 0. So you cannot be pi over 2. Pi over 2 is outside the domain, so you cannot do it. So what do you do to make that observation? Well, for less than pi over 2, you probably would choose 88 degree, 89 degrees, so on and so forth, right? For larger than, you probably choose 91 degree, 92 degrees, or 90.999 degrees, right?
Yeah.
Do you hear me? So
Yeah.
that's how you make that observation. That's how you're going to make that observation. And numerically, it can be done. So you understand what I'm saying, what I'm talking about. So now I'm going to make that table so you would understand why I make that table that way. Okay, so now I'm going to make that table. Okay, we don't need so many columns.
I have class very soon, by the way.
Okay, but I just give you the hint so you can work it, right?
Yeah.
So to observe this piece, you will probably choose the values of, because this is less than pi over 2, you probably choose degree-wise, like 89 degrees. I think you'll get it, 89.99 9 degrees. And you observe the tendency. You know what I mean?
Yeah.
89.999 degrees, if you wish. For the other one, okay, you would probably choose 90.1 degree, right? 90.01 degree, you know what I mean?
Yeah.
So you are approaching 90 degrees, getting closer and closer to 90 degree from smaller than 90 degree in here. And this side, you approaching 90 degree from larger than 90 degree to observe for yourself. So this second column will be this secant A. So you're going to look at those ratio then you will draw your conclusion.
Okay. Do you think you can do the first two and then I can do the rest?
These two?
No, like do the 89 and then do the 90.1.
Okay. So what will be secant? So for example, if I do it, right? Let me see if my software do this, right? So if I do secant of 89 degrees, okay, I don't know if the software will do it. It does, right? So it gives me this number, right? For the 90.1 degrees, is going to be, it's giving me, so 90.1 is going to give me, let's see what's it give me. Okay, so you're going to keep getting numbers, but I will guess these numbers are getting larger and larger, and these numbers are getting smaller and smaller. So the conclusion would be what? In this case, secant is going to approach positive infinity, and in this case, it's going to approach negative infinity. So I have just illustrate to you how to analyze. It is the how that's important to you. Do you understand what I'm saying here?
Yeah.
And you can do similar analysis at a negative pi over 2. Right? You can do similar analysis at negative pi over 2. Right? So this could be negative pi over 2. Right? And of course, I wouldn't know the conclusion. I would leave that for you. Right? So this is going to be negative. And this is going to be what? Negative. You see how that's been done? Is typically you analyze the situation between at the border of domain and non-domain. That's where the analysis is done. And that's what calculus spend a lot of time when they study limit and continuity, they spend a lot of time on that. But how do you figure out those points, right? The domain tells us. So this similar analysis can be done for cosecant. Cosecant has a different domain, multiple pi. So you'll be in the border between 0, between pi, left and right, 0, left and right, and so on and so forth. Mm-hmm. That's what you do. Does that make sense to you?
Yeah.
So there is a systematic method to do it. And there's a systematic notation to denote it. Do you have to go? If you have to go, just let me know.
Yeah, I kind of do have to go. It's going to start pretty soon.
Okay, but I think
it starts at 10:20.
All right, so I think now you kind of understand the idea, right? Mm-hmm. And so work on it. If you have more questions, and feel free to come back.
Do you think we can go over this on Thursday? Because I won't be back because the thing that my classes start usually when your office hour starts. That's why.
Sure. Because
I